Hello and welcome to the Radiation Basics Training. My name is Armin Ansari. I'm a health physicist at the Centers for Disease Control and Prevention. Now, if you're participating in this training, you may be a public health professional, a clinician, a law enforcement official, a first responder, or someone who wants to know more about radiation and radioactivity. And you are in the right place. Now, the word radiation carries a negative connotation for many of us. It's not something we want in our lives generally. But the truth is that radiation is all around us every day. We're exposed to radiation constantly, from radiation that comes to us from outer space, elements in the ground, the food we eat, and the air we breathe. And these everyday exposures don't do us any harm because our cells and our bodies have evolved and adapted to living in these conditions just like any other life form on Earth. So it's important to keep this context in mind as we explore and evaluate additional exposures to radiation. Now, this training gives you a basic understanding of radiation and radioactivity and prepares you for more advanced training. Radiation Basics is divided into 8 segments. In these segments, we will discuss sources of radiation, radioactive decay, measuring radiation, biological effects of radiation, radiation protection, decontamination, environmental impact of radioactivity, responding to radiation emergencies. Now, after you complete this training, I invite you to visit our website where you will find additional resources and training products. And if you have any comments on this particular training or other products you see on our website, please email us your comments. Now, thank you again for your interest in this topic, and let's get started. Now, in this training, whenever we talk about radiation, we're really talking about ionizing radiation. So let me first describe to you what radiation is, and then tell you what's different about ionizing radiation. Radiation means energy that originates from a source and then travels through space at the speed of light. And this energy has an electric field and a magnetic field associated with it, and it has wave-like properties. So a more technical term for it would be electromagnetic wave, but we just call it radiation. The most familiar form of radiation is actually visible light. Visible light is electromagnetic waves. It's energy that originates from a source and travels through space at the speed of light. It has wavelengths and frequencies that defines its energy. And if we're blessed with good vision, we can actually see this radiation. We can detect it with our eyes and see this radiation. And the difference between colors of light, red, green, blue, and so forth, is in their energy, wavelength. That's what sets them apart, and that's how we can detect them. So different colors of light are actually radiation of different energies that we can see. Now, the spectrum of visible light that we see, the range of visible light, the different colors, is only a tiny fraction of the entire spectrum of electromagnetic radiation in nature. The nature has radiation with energies that are far less and are far higher than visible light. So if we start in the range that we can see, and start with red, which has the lowest energy. Red light has lower energy than blue light. So let's say we start with red and go down in energy. We go to infrared, microwaves, radiation from cell phones, radio waves. These are all forms of radiation that have less energy than visible light, and of course they're invisible to us. Now, if we go higher energy, let's start again, come back to the visible spectrum and go to blue light, which has a higher energy, and then purple. Then we go to ultraviolet and X-rays and gamma rays. And these types of radiation have much, much higher energies than visible light. And of course, we can't see them. But we have detectors, instruments that can detect these types of radiation. And in other segments, I'm going to show you how we do that. But we have instruments that can detect these types of radiation. Just like we have instruments that we can measure the intensity of visible light. We have light meters that do that. We can detect it with our eyes, of course. And then radios. Radios, we can tune into frequencies in the radio frequency and do that. So we have instruments to detect all types of radiation. In fact, it's interesting because at any moment, all the radiation signals that carry information for all our favorite radio stations and television stations are all here in this room. It's just a matter of having the right instrument to tune into it. I want to talk about ionizing radiation, which is X-rays and gamma rays. So what happens at the higher energy side of the electromagnetic spectrum, these forms of radiation interact with matter. They have enough energy to remove an electron from an atom. And when they do that, the atom becomes charged or ionized. So that's why we call these ionizing radiation, because they have a capability to ionize atoms when they interact with them. This is a unique property that is these other forms of radiation, including what we get out of a cell phone, don't do that. So in this training, we're going to focus exclusively on ionizing radiation. Even though we might just say radiation for simplicity, what really mean is ionizing radiation. So where does ionizing radiation come from? Well, in our nature, ionizing radiation comes from radioactive atoms. And radioactive atoms, just like any other atom, as you know, are building blocks of matter. So it could come in solid form, it could come in the form of gas, like this, or liquid. So just like any other matter, radioactive material or radioactive atoms are part of matter. They could come in gas, liquid, or solid. But what makes an atom radioactive? As you know, atoms are composed of a nucleus and have a cloud of electrons that surround them. In the nucleus, we have protons and neutrons. And there needs to be a good balance between protons and neutrons for the atom to feel stable. Let's take carbon, for example. Now, carbon has 6 protons and 6 neutrons. And that's a pretty happy carbon atom because it's pretty stable. Proton determines what the identity of the atom is. So if you take the carbon atom and we add an additional proton, 7, it's no longer carbon. It becomes nitrogen. Nitrogen has 7 protons. And nitrogen likes to have 7 neutrons to be happy and stable. Often you see in this training also, we will follow the name of the element with a number. Say nitrogen 14 or carbon 12. That number is the atomic mass number, is a summation of protons and neutrons, the sum of protons and neutrons. So that number, that's what it refers to. So nitrogen with 7 protons and 7 neutrons is a stable nitrogen. Nitrogen 14 is happy. Carbon 6 and 6 is a stable carbon atom. But carbon 14, which we see in nature and we'll talk about later, has 6 protons, which makes it carbon, but 8 neutrons. So it has 2 additional neutrons, and that's an unstable nucleus. And it's radioactive. Because unstable nucleus doesn't like to remain unstable, it likes to reach a more stable state. And what it does is eject some of that extra energy, ejects it out to reach a more stable state. And this process I just described is radioactivity. So let's discuss some key terms. Radioactivity then is the spontaneous release of energy from an unstable atom. Radioactive material could be a solid, liquid, or gas that contains radioactive atoms. And radiation is the energy that comes out of the radioactive atom. Radioactive isotopes, and sometimes we call that radionuclides, are radioactive atoms of the same element that they have different numbers of neutrons. An example would be iodine. Iodine 131 or iodine 125. Now these are both iodine, element is iodine, but they have different number of neutrons and they're both radioactive. So we call these radionuclides or radioactive isotopes. And then radioactive decay is that process, the change, going from an unstable atom to a more stable atom by emitting radiation. So the carbon-14 that I mentioned earlier, the carbon-14 atom would go through a radioactive decay process, expel some of that extra energy, and change back to a nitrogen-14. So carbon-14 will go to nitrogen-14, which is a more stable atom. Uranium, also we find in nature, uranium would go through radioactive decay process and transform into an atom of thorium, which is a more stable atom. But sometimes even the atom that it transforms into still needs to go through more processes. So thorium is still radioactive, has less energy than uranium, but it still needs to go through a few steps of radioactive decay. So I'm talking about now a lot of different types of radionuclide, uranium, thorium, carbon, nitrogen. We actually have quite a lot of radioactive material in our environment that occur actually naturally. Most of them occur naturally. One group of radioactive atoms, we call them primordial. These atoms were around when the solar system and the planets were formed. These include uranium, thorium, and potassium. So they were around, what we find today, they were around when the planet was formed. I want to talk about potassium a little bit because all of us know about potassium. Potassium 40 is radioactive, but potassium 39 is the stable one. Stable potassium has 19 protons and 20 neutrons. That's the balance of proton and neutron that makes it happy. So a potassium with the number 39, that's the stable. And out of every 10,000 potassium atoms we found in nature, 9,999 are potassium 39. But 1 in 10,000 has an extra neutron, which makes it potassium 40. And that is a radioactive potassium because it's a little bit unstable. So it needs to get rid of that extra energy to become more stable. Now, potassium 40 happens to be a patient atom because it takes it about 1 billion years to do that on average. The half-life of potassium, we'll talk about half-life later, but it takes it more than 1 billion years to go through that transition and become a more stable atom. Now, some of our foods, I'm sure many of you like bananas. As you know, banana is rich in potassium. Anything that has potassium, it also has potassium 40. Because out of 10,000 atoms, one of them is potassium 40. So we have actually plenty of potassium 40 atoms right here in these bananas that we eat. Our bodies, we have potassium in our bodies, and we have potassium 40 in our bodies. And we can actually measure the radiation that we emit because of that. The other group of radionuclides we have in our nature, we call them cosmogenic. And that means that when we have cosmic rays coming to us from outer space, these cosmic rays interact with atoms we have in our environment, particularly in our atmosphere. And they create new species of radioactive material. A good example, we have plenty of nitrogen in our atmosphere. And cosmic rays interact with nitrogen and make carbon-14. Remember, carbon-14 is a radioactive carbon. Carbon-12 is a stable one. So carbon-14 is generated in our atmosphere when cosmic rays from outer space interact with nitrogen in our atmosphere. And this carbon-14 over time becomes part of our nature, incorporated in our environment, and becomes part of every organic life on Earth. We all are carbon-based. That means we have carbon. In fact, 1 out of every trillion carbon atoms is a radioactive carbon. So we have carbon-14 in our bodies and anything else that's organic. Now, you're familiar with carbon dating. That's based on this principle. The reason we can do carbon dating is because anything that has carbon in it, we know has carbon-14 in it, and we know the half-life, and we can estimate the approximate age of whatever it is that has carbon as part of it. The last group of radionuclide I want to talk about, they're called man-made. We call them man-made because, as the name implies, man-made them. They're through human activities that we have them in nature. One example of that would be cesium-137. Cesium-137 does not occur naturally in our environment. It's actually a byproduct of nuclear fission. And the cesium-137 that we find in our environment are remnants of atmospheric testing of nuclear weapons in the 1950s and 60s. Cesium-137 was part of that nuclear fallout, and now we have it has become part of our environment. Small amounts have become part of our environment. We use this knowledge of how to produce new species of radioactive material actually to our benefit too, because many of the man-made radionuclides we produce today are intentional because they have either applications in medicine, industry, or research. Another man-made source of radiation I should mention is those that are machine-generated. They don't come from radioactive materials, they're machine-generated, and you all know about them. X-ray machines and CT scanners. In those machines, there's no radioactivity, but they use electricity to generate ionizing radiation. But once they generate it, those ionizing radiations have the same properties as the ionizing radiation that we get naturally from radioactive material. But the generation is through a different mechanism, and there's no radioactivity involved in there. So now we're talking about lots of stuff, lots of radioactive material, lots of radiation coming from everywhere. So the question, how much are we getting from all of these sources? What we call the amount of radiation is the dose. And we measure it in units of millisieverts. In the United States, an average person receives 3 millisieverts of radiation from natural sources, from the cosmic rays, the ground, the food, and everything. 3 millisieverts. Of that 3 millisieverts, 2/3 of it, on average, comes from radon. Radon is a radioactive gas that occurs naturally. and has its origin actually to the uranium in soil, the breakdown of uranium in soil. So it's a naturally occurring radioactive material that is in form of gas. So when I showed you earlier the balloon, this is actually technically has radioactive materials in it because I exhaled in it. When I blew the balloon, I said, and I exhaled. Every time we breathe in some radon, and then I exhaled, and some of those got trapped in the balloon. So technically, we do have radioactive atoms here in the air that we breathe. And of course, region to region, place to place, sometimes even with radon, home to home, there's variation. So we always have variation in the amount of radiation we get from natural environment. But on average, we get 3 millisieverts of radiation from the environment. That's living on Earth. On average, we get another 3 millisieverts from medical procedures. And a lot of us are getting X-ray exams, CT scans, and so forth. On average, that contributes another 3 millisieverts. 30 years ago, that was less than 1 millisievert, but now it's close to 3 millisieverts because the technology has advanced, so we're using that technology more. So total, on average, 3 millisieverts from the environment and 3 millisieverts from medical exposures. That gives us 6 millisieverts average annual dose to a person in the United States. Individual doses can vary. So many factors can influence your individual dose. If you smoke, the dose to your lung is actually quite significant, radiation dose, because of the radioactive material that's in tobacco. So smoking increases your radiation dose to your lungs. If you live at high elevation, say Denver, Colorado, you get a higher dose from cosmic radiation than if you live near the coastline. So where you live makes a difference. If you share a bed with someone, with your spouse or a partner, remember our bodies contain radioactive material and we actually measure radiation coming out of our bodies. We irradiate all the time. So when you're sitting next to someone, also you're irradiating each other. So obviously those who share a bed, they get a little extra radiation dose just because they don't sleep alone. So these factors, now that's a small factor, but there are these other factors, smoking, high elevation, and also other activities that would increase your individual dose. In this chart, you see some of the typical doses associated with some common activities like air travel, chest x-rays, CT scans in units of millisieverts compared to what we get from our natural background. Now, the frequency of these activities, like air travel or medical procedure, would impact your total dose as an individual. So even though our average is about 6 millisieverts, as individuals, your individual dose could vary and could be actually much higher in any given year. Now, we talked about medical procedures, and in the chart I showed you doses for medical procedures. Now, this does not mean that we should avoid medical procedures like CT scans, because they have a clear benefit for us. Doctors, the imaging studies provide valuable information to our doctors to make diagnoses. So that's a clear benefit to us. So it's important to consider the risks and benefits of any procedure or activity that exposes us to ionizing radiation.